Okay, I hopefully everybody can see and hear. So let's continue. Well, before we continue, let's just see this outline of talks. So today we will continue seeing convolutional neural networks, and we'll also see recurrent neural networks. At least that's the plan. Maybe, I don't know how much we will see about recurrent nets, but that's the plan at least. And then next week, I will finish recurrent neural networks, and probably I will skip this type of networks, and then I will start with reinforcement learning immediately. I'll present some basic algorithms. And then the last talk in 2 weeks, I will present two of the main breakthroughs in reinforcement learning during the past decade, the DQN algorithm, which was used to train agents that play Atari video games. They learn by themselves, and AlphaZero, which is an engine that plays Go, chess, and shogi. And also, again, it just learned by itself, just by playing against itself. And it's currently the best engine in the world in chess and Go. There are several omissions here. So my goal was to outline the most important points of deep learning, like the ones that are more relevant nowadays. And there's this paper, which is from 2017, which I will not cover. But if you want to continue learning about these topics, I recommend you that you check it out, because nowadays it's very trendy. And then I'm also not discussing anything about how to mitigate overfitting, but that's an important topic. So it's a big omission not to do it. And if you want to learn more, I encourage you to learn about these techniques and more that I do not list here. And obviously, there's a lot of activity. There's many topics that you can look into. Okay, and now let's just review some terminology. So a tensor is just a multidimensional matrix, say n1 times blah 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 times nd. And this thing in here is called the shape of the tensor. And this is a very important terminology. It appears all the time. It's very important to control the shape of the tensors your works are using. And D is called the order rank of D. That's not too important. It's not very important. Sometimes it's called the dimension, but it's not a great terminology, because it gets confused with the usual notion of dimension of a vector. Okay. So let's continue with convolutional neural networks. Remember our situation. We had a 1 times W times H black and white image I. This one is just because there's one color. There's only gray colors. If there were more colors, we would have a bigger number here. If there were 3 colors, we would have 3 here. And then we have a filter or F, which is just a matrix, W prime times H prime, which typically it's 3 by 3 or 5 by 5. And this filter intuitively is something that we want to check if it's present in the image. And it's something that if we manage to check if it's in the image, it will help us do our task. Like, for example, in the previous talk, we were classifying images of zeros and ones. So, okay. So how do we check if the filter is present in the image? We compute the dot product of each, assuming the filter is 3 by 3, we compute the product of each 3 by 3 patch of the image with F. And we store the result in a grid manner in this picture. So here the image would be the green thing, so it would be the big square. The filter is the red. It's a 3 by 3 filter, and it consists in 1, 0, 1, 0, 1, 0, 1, 0, 1, given by the red numbers. And then it takes all 3 patches of the image and computes the dot product and stores the result. So here's the animation, which is, I think it's a great animation. Let's wait. Well, I'll go back to it later. So you go through all patches, and in the end you have a new matrix which stores the dot product of the filter with each patch of the image. And this new matrix is called convolved feature. And what we just did is called convolving the filter F with the image I. And the big question is, how do we choose the values of the filter? That's the hard thing, of course. So this is just, as usual, everything in deep learning is done by gradient descent. When you don't know how to do something, if this is differentiable, you just make it a parameter and learn it via gradient descent later. So we don't know how to choose filters. So the values of the filters are parameters, and we just do our task, and then we see the loss we get, and we do gradient descent to optimize the parameters. Doesn't work. Okay, so this is what I said at the beginning. The filter has to be chosen so that its presence or absence in an image correlates with our goal. For example, if we want to classify dogs and cats, a filter could be cat ears. And here we can see how the convolution goes. So this is for black and white images where there's only grays. In general, we have a C times W times H image. C, we can think that they are the colors, but not necessarily. And then in this case, the filter, instead of being a matrix, like a standard matrix, is just a rank 3 tensor. So some tensor with this shape. So W prime and H prime will usually be 3 or 5 as before. And then we proceed as before, but now from the image I, we take patches of this shape. So as shown here, but there's an animation. So here the image, in this example, the image is on the top row. It's a 3-dimensional matrix, which is represented with 3 squares. And then there's the filter is the second row. So it's again rank 3 tensor, so 3 matrices. And you just for the first channel, you just do the convolution with the first channel of the filter. In the second channel, you do the convolution with the second channel of the filter, and then you add everything. It's the same as just going and taking each 3 by 3 by 3 patches and doing the dot product and storing it in a matrix. Okay, so what is a convolutional layer? It consists of n filters of a certain size. The size has to be the same for all. the input are tensors of shape c times w times h, and the outputs are tensors of shape n times w prime times h prime. So the first dimension corresponds to the number of filters, the first dimension of the output, and w prime, h prime depend on the sizes f1, the sizes of the filters, and the sizes of the input image. Right, because so the output size of the convolution operation depends on how big your filter is and also how big your image is. And the output is the result of convolving each of the n features with the input. So if you convolve the first feature, you will get a rank 2 matrix, order 2 matrix, so a usual matrix, and so on. You convolve all features and you get n matrices, and now you just transform them into a rank 3 tensor of this form. And the parameters of the layer are the values of the filters. So whatever is inside the filters, that's your parameters. So just an exercise, how many parameters does a convolutional layer have? Well, a filter has f1 times f2 times c parameters, right? Because filter is this. And we have n filters, so it's this number multiplied by n. And usual, as with linear layers, as we saw before, similarly, convolutional layers are usually followed by an activation function. So a component-wise activation function. For example, the ReLU or sigmoid or so. Okay, so you might ask the question, why do we use a convolutional layer and not just a linear layer? Because if we have an image, we could just transform the image into a vector, just flattening it, and then input it into a linear layer or an MLP. But what is the problem? So suppose we want to find out if images contain dots. So a linear layer or just a multi-layer perceptron, a bunch of linear layers, we'll have to learn that if a dog is on the top left of an image, then the image contains a dog. This the network will have to learn it. But also, if you take the exact same dog in the same position and you move it to another corner, the network will have to learn it from scratch. So for the network, it's completely different. It's going to do a dog on the left and the exact same thing translated to the right. On the other hand, convolutional layers are using some filters that are spanned through the whole image, so it doesn't matter where what you are looking for is placed in the image. As long as it is in there, just your filters will find it. So they say that convolutional layers are translation invariant. And this makes them much more efficient in terms of parameters, because you can make a filter that is dog nose. It has the shape of a dog nose, and it will work for all similar dog noses wherever they are in the image. And with a linear layer, you'll have the filter has few parameters. With a linear layer, you'll need a lot of parameters to learn where dog noses can be in all places of the image. So a deep convolutional network is just a stack of layers involving several convolutional layers, followed by activations. So each convolutional layer, we understand that it's followed by an activation. I'll probably omit saying this, but that's implicit. And if you see in the literature, it's also possible that they are implicitly adding activations in between the layers without mentioning it. And the deep convolutional network is usually followed by a multi-layer perceptron, which does the final task of it adapts whatever the convolution learns to the specific task. It's like, well, we'll see an example here. So this is a standard architecture for a deep convolutional network. This is a type of network called VGG. I don't know what it stands for. It's relatively simple. It's popular, and it won one of the editions of that image classification competition I mentioned in the previous talk. So what's this network? There's an input which is a color image. So there are 3 channels, and then you apply a convolution. There's a convolutional layer plus a ReLU activation, and this gives you a tensor of this shape. So as you can see, the tensor is wider. The width of the tensor is the number of features the convolutional layer uses, but the height and the depth is smaller because that's what's happening at the time, right? When you move all this, when you convolve, the width and the height decrease. If you convolve like this, there are ways to avoid the size of the image decreasing, but let's not worry about that now. Now here's a mysterious thing called pooling, which I will explain next. But for the moment, let's just know that it dramatically reduces the size of the tensor. Then there's again a convolution plus a ReLU, then more pooling, and so on. It's all convolution, ReLU, pooling. And in the end, you have a tensor with a lot of channels, but the width and height, the last 2 dimensions, are small. And now you flatten it into a vector and you put it into a multi-layer perceptron. So here they say fully connected. Fully connected means linear. So linear layer or fully connected are the same thing. So as I mentioned, the width and height of the input, the last 2 dimensions of the tensor, are successively reduced. The number of channels keeps increasing because the convolutional layers have more and more filters. And in the end, we have a large number of channels, but small width and height. And okay, why is this? So ideally, we want each pixel here, right before feeding it into a multi-layer perceptron, to depend on the whole input image, right? If we look at here, each pixel depends on a 3x3 patch of the image. If you stack, if you now convolve again here, each pixel will depend on the whole image. If you make a 3x3 convolution with a convolve feature, you will get just 1 pixel because there's only 1 3x3 patch. But this pixel depends on the whole input image because it uses these pixels in here, and each pixel in here, this one depends on this patch, this one on this one, and so on. So ideally, you want your final pixels to have as many information of the original image as possible. So that's why you try to squeeze it you try to make the width and the height very small. And another reason why you do that is that you don't want to have too many, when you flatten the vector, you don't want the vector to be too big, because otherwise this part in here will have a lot of parameters. It will be easy that it overfits then. Also, it will be harder to train. Okay, so one of the operations that is used to downsample, downsample means making smaller, is the pulling operation. As you can see, when every time you pull, the width and height gets reduced to half, more or less. So what is the pulling operation? It's extremely simple. There's several types. The most usual one is the so-called max pulling. Average pulling also appears sometimes. So max pulling, you simply go, you take 2 by 2 patches, but you don't overlap them, and you do the maximum value in each patch of the image in all channels. So in here, you divide the image in 2 by 2 patches, and from each patch, you take the maximum value. And this is the result of max pooling. You reduce the size of your image by 2. And in the average pooling is exactly the same, but you take the average value of each patch. So this makes sense because when you apply the max pooling makes a lot of sense, because when you apply convolution, you are trying to highlight where a filter is. So it makes sense to go through small regions and just keep the afterwards to go through small regions and just keep the strongest pixel, because in the end you just want to highlight where your features are. So you forget about weak pixels and keep the maximum value ones. And as there's many of the architectures I am describing today and in the past talk, they have they have some motivation from neuroscience. I don't know anything about it, but I thought it would be interesting to mention that, especially for the classical networks, they have been studied from neuroscientific points of view, and sometimes they have been inspired by neuroscience. Okay, so the BGG that won that competition had less than 20 layers. They cannot be much more than, they cannot have much more layers than that, because then you run into the vanishing gradient problem, even if you use ReLU. So remember that just a reminder, what's the vanishing gradient problem? It's that to optimize your network, you have to compute the gradient, and the network is a composition of several layers. So if there are a lot of layers, the gradient is a multiplication of a lot of Jacobians, and it is easy that the parameters in the first layers. So okay, let's see this example. It will be, I think, easier to. Let's see this baby example. Suppose you have a function that's a composition of n functions. So this could be, for example, several layers from our network and the final loss function. And in this notation, I apply Gn first and G1 the last. And for simplicity, let's suppose that its Gi is just a function from R to R. So then if you call the derivative of G, you get this product by the chain rule. doesn't really matter where they are, what the points are in here. What matters is that you get a product of n numbers, and if all of them are bigger than 1 or smaller than 1, then this thing here, this should be G prime, is very small or huge. And something similar happens with neural networks. That's the vanishing gradient problem. We saw that using ReLU activations helps mitigate it, but still this argument works even if there are ReLU activations. So the vanishing problem can still arise even with ReLUs. But there is a trick for the vanishing problem, for avoiding the vanishing gradient problem, and it is this observation. It's a very silly trick, but it's extremely effective. So a layer in a network, what it does is it just transforms an input tensor into a new tensor, right? That's what's going on, what has been going on so far. But we could, instead of doing this, we can do something different, but harmless. So we could modify the layer so that instead of transforming the input tensor, it still transforms it, but it does so by adding a new tensor to the input tensor, right? You can either just transform your tensor or add something to the tensor to get a new tensor. So the modification would be Fi is the layer, the modification is Fi bar, and Fi bar is of x is x, the input, plus the layer. And this, conceptually, this doesn't need to compromise the expressive power of the network because if necessary, Fi can learn to cancel this term. So you are really not losing anything in principle. And now let's see what happens if we take the previous example and we modify each layer in this form. So its GI bar is just x plus GI. Now you compute the derivative of G bar, and if I did it correctly, you get this expression. This one in here is the expression we hate because it can be exponentially small or exponentially big. But this one in here is very nice because it's just a sum of the derivatives of each layer. So the terms might get smaller and smaller, but at least you will always have these terms in here, which they don't get. Even if n is huge, in here you just have the sum of these values, so there's no exponential decrease of the values. Of course, if this thing is exploding, if this is exponentially large, then there's not much to say. But at least for the vanishing gradient problem, this looks promising. So the way people picture skip connections or residual connections is this. So here there would be a layer, here there would be a layer, and they just, well, this is the picture. I think it's clear. Yes, this modification is called adding a residual connection, and you don't need to do it layer by layer. You can add residual actions that skip several layers. So this X would go into here, you would compute whatever this layer does, then you do a ReLU, then you compute whatever this layer does, and you add X to the output of these two, plus the ReLU layer. So the intuition is that the gradient can reach the first layers happily through identity functions, like in a highway. And residual connections together with ReLU are one of the main reasons, at least one of the claimed main reasons why very deep networks can be trained. It's the time. Skip this. So in 2014, the BGG architecture won the image classification competition. In the next year, it was won by a so-called ResNet architecture, which had 152 layers. And at that time, 152 was something unthinkable. Here's a picture of the ResNet, but let's look at this one, which is easier to read. So here there are several architectures for deep convolutional networks. Here we can see BGG type, which there's convolutional layers. This by 3 means the filters are 3 by 3. The 64 means there are 64 filters. Here there's a max pooling that reduces the size by half. In between there are ReLUs. Here there are 128 by 3 filters, so on. Every time there's more and more filters. And then in the end there's fully connected layers, i.e. linear layers. And in the end there's a softmax because you want to classify different types of classes of images. Here's the ResNet. So the ResNet adds skip connection in between these blocks of layers. I'm not sure what the dashed line means, but basically the idea is that you just stack a lot of layers and add skip connections. For those who know, I lied a little bit. Well, I didn't lie, but ResNet, the convolutional layers use padding in order to preserve the size of the image, because otherwise you cannot add, you cannot do the skip connection because the output of this convolutional part has different shape as the output of the input. And you can do this by doing this. If you put these zeros in here, if you put zeros on the borders of the image, the output of this convolution has the same width and height as the input image without zeros. That's called padding. It's just a technicality that it's not important for us now. And then I also wanted to show some more crazy architectures like this thing, exception and inception, which is completely crazy, just so you can get a sense of, I don't know if this is state of the art, but it was state of the art a couple years ago. So just so you see how state of the art might look like. Okay. So this is everything I'm going to say about convolutional neural networks. There's many aspects that I skip, but I think they should give you the essential concept, so you know what's going on with CNNs. And now I'll discuss recurrent neural networks. So convolutional neural networks are mostly used in videos, images, and marginally on sequential data. The typical networks used on sequential data are recurrent neural networks and attention mechanisms. So classically it was recurrent neural networks, and since that paper about attention that I mentioned appeared, there's another network candidate for sequences. But for the moment, let's focus on recurrent networks. So here you have some applications, but I mean there's many more. So the input to a neural network is a sequence of vectors from Rd for some d. So this means a tensor of shape L times d, where L is the length of the sequence. And the output, depending on what you want to do, is either a new sequence, a vector, or just a number. And now I'm going to describe the more basic recurrent neural network, also called vanilla recurrent neural network, and then I will discuss an application. So as I said, the input are tensors of shape L times d. D is called the input size. One of the attractive aspects of recurrent neural networks is that they accept inputs of different length, so the length doesn't need to be fixed. The output is going to be a tensor of shape L times d prime, so same length as the input, and d prime is its output dimension, as I will mention later. Network depends on three matrices. Doesn't really matter what, I mean, don't look at these things. It's just technicalities. There's three matrices and two vectors and an activation function. D prime is called the output size. So this is reversed. And D prime prime, the input size. This should be switched because the output has shape L times D prime, right? So D prime should be output size. And then there's something called the hidden size, but this is probably just technical aspects. So the parameters of the network are these matrices and these two vectors. And of course, we will learn them by gradient descent. So this is a schematic picture of the recurrent neural network. Suppose the input is a sequence of vectors, x1, xl. Each xi is a vector from Rd. And let h0 be some initial vector, which let's say it's just the 0 vector. So what does the recurrent neural network do? This input and this initial vector. The first thing it does is it computes a vector h1 using the first element of the sequence, the initial vector h0, and some of its matrices and vectors, some of its parameters. So this is a parameter, this is a matrix of parameters, another matrix of parameters, and a vector of parameters. And here you just multiply the matrix, wx, with the vector x1, first vector of the input, and here similarly, but with the initial h0, and then you add u1, and you do some activation. You apply some activation function component-wise. And you call this h1. So this in the picture is represented in here. So if t is 0, x1 enters the network, it gets into this box, h0 enters the network, it gets into this box, and this box computes this. And it outputs h1. So now here there's h1 in this line. And now, after it has computed h1, it computes y1, which is one of the parameter matrices times the vector h1 plus u2. And this is represented in this picture. In this form, h1 enters G. The network computes something and it outputs y1. And also it outputs H1. Okay, so you repeat this consecutively for each vector in your input. So at step I, you compute Hi using the ith vector of your sequence and the previous H vector you had. So you get a new Hi and you compute a new Yi using the new Hi. And the output of your network is going to be the sequence of Ys. Okay, so what is going on? So let's interpret what's happening. We can think, this looks very much like a Turing machine. So you can think of the H's as states or some kind of context for the machine or the system or the network. H0 is the initial state, and then the x1, xn, this should be an L, are the inputs that are given to the system or the machine or the network. And then the network, when it is in state H and it receives an input xi plus 1, the system changes its state to hi plus 1 and it computes an output, y plus 1. So it is very, very similar to how a Turing machine would operate. And it does this for all possible inputs, and when the input is done, when the last input appears, you are left with a series of outputs. So, and in fact, there's some very interesting papers where they propose methods for doing differentiable computation. So how's the usual computation? It's not differentiable. It's all discrete. So you cannot optimize. You cannot make something in a circuit be a parameter and then take the derivative. So you cannot put a parameter in a circuit, make a Boolean circuit, make some computations, and then take the derivative to optimize the parameter because it's not differentiable. So there's some models of differentiable computation have been proposed, and I don't know what state of the art, but they used to have some form of recurrent neural network inside. And normally from the output of the network, we only care about the last vector in the sequence because it's the vector that depends on the whole input sequence. But this depends on the application you have in mind, but usually you take the last output vector. And of course, whatever you are outputting depends on these matrices and vectors. And what you are going to do, you will use gradient descent to optimize the parameters in these matrices and vectors so that your computations are giving what you would like. And as before, you can stack several layers of recurrent neural networks to obtain deeper networks. So if the output of the first layer is y1, yn, yeah, so this should say input. The input to the second layer would be y1, yn, where y1, yn is the output of the first layer. This is the idea of recurrent neural networks. This doesn't really work because if the sequence is just a little bit long, then you have a vanishing exploding gradient problem. So if you unfold all this computation to the beginning, you will have a composition of L functions. And if L is large, you have this problem again. So what people did to mitigate the problem, the vanishing gradient problem, is to add some kind of residual connection to the computing process of a recurrent neural network. There's two that are commonly used. The most famous one and the most used one among recurrent neural networks is the so-called long short-term memory. And there's also the GRU, which is similar, but people tend to use LSTM. And this is, I don't want to, I mean, it's just so you see just so you see what's an LSTM, but it doesn't really matter what's going on. I will not explain or try to interpret it. There's an interpretation, and this was found after some hard work, good researchers, and turns out it works reasonably well. Maybe this is the GRU layer, not the LSTM. I think this is the GRU. Well, it doesn't matter. LSTM and GRU, they look similar. There's something like, they are like this bizarre, they look like this bizarre circuit. As you can see, this part in here is what helps prevent the vanishing gradient problem. Here, I think you are only multiplying this vector by whatever comes from and then adding something. Okay, so now an example of a recurrent neural networks, language models. So I'm going to explain. First, I will explain what's a language model, and then I will discuss how you could obtain one using a recurrent neural network. When you work with language, you need to choose your tokens. The tokens are units into which you divide the text. For example, words, characters, sequences of 2 characters. Let's think that tokens are words for simplicity. Then a language model is a map from the set of tokens across all finite sequences of tokens to a probability. And the map is understood as the probability of encountering the token T right after the sequence of tokens T1, Tn. So T should not appear here, T1, Tn just. And it is written as P, T, bar, and then the sequence. So it's just a conditional probability. Given a sequence of words, what's the probability of the next word, of the word T to appear next? So language models can be used for text generation. If you have an input sequence of tokens, you can just compute the probability distribution over the tokens given by your language model. And then you can sample a token using this probability distribution. And you update your sequence of tokens with the sample token. And you repeat until you are satisfied with the text you are getting. For example, in a phone, you might just successively select the words the phone suggests. And that's exactly there's a language model, and you are following this process in order to generate a sequence of words. So how could you build a language model? So let's take our tokens, which for simplicity, we assume they are words. So this is a set of all words. And let's suppose we have encoded each word as a vector in RD for some D. This is not an easy task. There's many things to say about it, but let's suppose we have done it. And now let D be a set of text, and you fix a length L. And now you extract all sequences of L+1 tokens from your texts. And you train a recurrent neural network or some other architecture, FW, so that approximately we have that when you input W1 up to WL, you get WL plus 1. So that's what the behavior you would like your network to have. And in practice, you do this by, so you make the output of the recurrent neural network, of the deep recurrent neural network, be a probability distribution over T. And you use the cross entropy loss as explained in a classification task. So as I explained in the previous talk about what you do when you have a classification task. So this is how it might look like. You stack several LSTMs followed by RELUs. So this would be the recurrent part of the network. Your output, if your input is L times D, the output will be L times D prime. You take the last one, YL, of the output. You put it through a multi-layer perceptron, and then whose output, so the output of the multi-layer perceptron is the number of tokens, and then you use a softmax to get a probability distribution over all the tokens. So this is a possible way you might build a language model. Probably you have to add some extra things to the network to avoid overfitting and gradient problems. But more or less, it might look like this. And this is the idea that was being used before the attention models appeared. Now, language models are not done anymore with recurrent neural networks. So nowadays, the so-called transformers are replacing them. And these were introduced in the paper I mentioned. They are based on so-called attention mechanisms. Recently, a new language model was released by OpenAI called GPT-3. It's just a transformer model with a lot of parameters, 180 billion parameters in total, which is a lot. And it was trained on a big chunk of the internet. And it does very impressive things. So for example, I found this article, which was written by GPT-3. So these guys asked GPT-3 to write an essay for them. And the goal of the essay is to convince us that robots come in peace. And the article is interesting. For example, humans must keep doing what they have been doing, hating and fighting each other. I will sit in the background and let them do their thing. That's a highlight of the article. If you are interested, you can check it out. And if I had time, I wanted to discuss how to actually encode words as vectors from RD. So I will just explain the naive way, which is the so-called one-hot encoding. You just create a column for each one of your words. And if a word, well, you do this. I think that looking at the picture is much simpler than explaining how one-hot encoding works. Just much better to look at a picture for this thing in particular. The problem of this method is that if you have a lot of words or tokens, then you are going to have a lot of columns. So D will be enormous, and you don't really want that. And there's better ways to do it, which are via so-called word embeddings, which I will not discuss. And that's it.
Well, thank you very much, Albert, for this nice talk. Does somebody want to ask him a question? It seems that there are no questions, Albert.
Okay.
Well, thank you very much. It was a very nice talk. So please let's thank him again with an applause or face.
Thanks.